Welcome to EDU World Space.
Sample problem 5, we first want to calculate the velocity of B at the maximum elevation. So let's write down what we know. At maximum elevation, ball B is at rest relative to cart A. And then VB is equal to VA. So when ball B begins to move, it moves with the same speed as cart A. So we will first use the impulse momentum principle and calculate VB. So let's draw a diagram of the situation. So our cart, in this case, is given an initial velocity v0. So the initial momentum of the cart is ma v0. And the ball is initially at rest. The impulse acting on the cart is due to the reaction from the track. So this is R times t, where R is the reaction, or simply the integral of R dt. The impulse acting on the ball is due to its weight. So this is the integral of its weight, W dt. So these are vertical forces. There are no horizontal impulses in this situation. And finally, the cart moves off to the right in our case with velocity ma, with momentum ma times its velocity va. The ball reaches its maximum height and moves off with final momentum mb vb. So if we resolve these into the x components, we can solve for vb. So the x components of the momentum impulse tell us the following. So initially, the momentum is only due to the cart. So that's ma v0. The x momentum of the ball is 0. And afterwards, the momentum is due to the motion of the cart, ma-va, plus the motion of the ball, mb-vb. And we can write this as ma plus mb into vb. Remember that va is equal to vb. So if we rearrange this equation, we can find an expression for the speed of the ball at its maximum elevation. And vb, if we rearrange the equation, is ma v0 over ma plus mb. So provided that we know ma and b and the initial speed given to the cart, we can calculate the speed vb at which the ball moves off. So now for part B, we've calculated the velocity of the ball at its maximum elevation. But what is this maximum elevation? Well, we'll now turn to the conservation of energy. The conservation of energy is between positions 1 and position 2. So energy needs to be conserved between these 2 points. So let's find the energy at point 1. The kinetic energy is due to that of the cart, since the ball is at rest. So that's a half ma v naught squared. That's the definition of kinetic energy. The potential energy at this point is 0. At position 2, the kinetic energy is due to the cart and the ball together. So that's a half ma va squared plus a half b v squared. We'll do some manipulation with this. So we can write this as a half into ma plus mb into vb squared. And we can write this in terms of v naught, since we know v naught. In essence, we should know v naught. That's ma squared, that is ma squared v naught squared from above over 2 into m a plus mb. So just substitute out and brought in v naught squared. So as you can see, if we don't know vb, we can calculate the energy, the kinetic energy, using v naught. And the potential energy at this point is the gravitational potential energy of the ball B at its maximum elevation, which we'll call h. So that potential energy is m mass of ball B times the gravitational acceleration g times its maximum elevation h. And the conservation of elevation tells us that the energy at position 2, v2, t2 plus v2, must equal to the total energy, total mechanical energy at position 1, t1 plus v1. And so if we substitute our values in this, we get that m a squared v naught squared over 2 into ma plus mb plus mb g times h is equal to a half ma v naught squared. So now essentially we only have one unknown here. The only unknown is h. So if we know the mass of the cart and the ball and the initial velocity given to the cart, we can rearrange this equation and solve for h. And if we rearrange and do some mathematics, we get that the maximum elevation reached by the ball h is equal to ma over ma plus mb multiplied by v naught squared over 2 times g. And that's the maximum elevation achieved by the ball.